Hey guys, it's Off-I-One here, and today we're going to be solving Pacific Atlantic water flow. In this problem, we're given a rectangular island that borders the Pacific and Atlantic Ocean. So we're given this 2D array here, and they're telling us that it borders the Pacific here, and it borders the Atlantic over here. Next, they tell us here that each coordinate here represents a height. So for example, this square here would be a height 5, this square over here would be of height 3. Next, we're told that the island receives a lot of rain, and when it rains, let's say it rains in this cell, the water can flow into the next lowest cell. For example, you can go to 4, but from 4, we cannot go to 7, because if you picture it, let's say this is of height 7 and this is a height 4, the water cannot flow upwards because that wouldn't make sense. So we're told that it can flow in all directions, that is not diagonal, so it can flow up, left, right, and down. So it can flow to the neighboring cells as long as the height is less than or equal to the current height of the cell. So for example, if we have two cells of height 5, the water can flow through that cell. In the end, they want us to return a list of grid coordinates that tell us which coordinates can flow into the Pacific and the Atlantic Oceans. So for example, let's say we start at this square here, 5. We can get to the Pacific Ocean by going from 5 to 3 to 2 and then into the Pacific Ocean. And this is a valid route because 5 is greater than 3 and 3 is greater than 2. So the water can just flow down from here into the Pacific Ocean. And we can get to the Atlantic Ocean a similar way. We can go from 5 to 1 to this one, and then we can go into the Atlantic. So we know that 5 can get us to both the Pacific and the Atlantic Ocean. And same thing for these other yellow squares here. So for example, there's 4 here. You can go to the Pacific by going to this 3, and then this 3 leads to the Pacific. Or you can go into this 4, and this 4 goes into the Atlantic. So the brute force way to approach this problem is to iterate through every single cell and then check if that cell can reach the Pacific and the Atlantic Ocean. So for example, let's look at this 2 here. We would go in all directions and we would check if any of these directions eventually lead us to the Atlantic and the Pacific Ocean. And if they do, then we want to add this to our result set. But there's a couple problems with this solution. First, there's going to be a lot of repeated work. So for example, let's say we do DFS for this 2 here. Well, eventually we're going to DFS for this 3 here, but we would already know the result based on this 2 DFS because we already went to the right. And because there's a lot of repeated work, our time complexity would be something like O of n times m squared. Because our worst case scenario would be, let's imagine all of these being 1s, then we will have to do DFS for every single one multiple times, and that would be O times m squared. Because we would go through every node and edge while traversing the graph. A linear time solution would be to separate it into Pacific Ocean set and Atlantic Ocean set. So for example, we would find the coordinates that can reach the Pacific Ocean, and then we would find the coordinates that can reach the Atlantic Ocean, and then we can find the overlap of all of them. So in the origin line here, I've circled the coordinates that can reach the Atlantic Ocean, and in purple here, I've circled the coordinates that can reach the Pacific Ocean. And we can see here that all of these squares here that are in the overlap are what we would return in our final result array. The reason this algorithm is going to be in linear time is because of the way we're going to implement it. For the Pacific Ocean part, we're going to take this column here and this row, and we're going to run DFS starting from each one of these coordinates here. And then we also aren't going to visit the same coordinate twice. So for example, if we do DFS from 3 and 2, we would land at this 2 here. But for the first iteration, let's say this was the first call to it, we would already include this in our set because we already know that we can reach the Pacific Ocean starting from this point. So this way, we would never visit the same node twice because we already know that the outcome is going to be the same. And one little thing I should mention is that as we're going to go from the Pacific Ocean inwards, we want to think about it a little backwards. So if you remember, for this 5 here, we only wanted to go to the other node if the other node was less than or equal to the current node. But for this now, since we're going from the Pacific inwards, we want to check if our current node is less than or equal to the next node. Because that way, that tells us that if we actually go in the right order, for example, here, that way, then this has to be greater than the previous node. So I know this sounded a little confusing, but hopefully it makes sense. Basically, we want to have the water go from the Pacific Ocean upwards instead of here and downwards. But it should be the same thing in the end. Okay, I got a little sidetracked there, but hopefully it all makes sense now. And also for the Atlantic Ocean, we want to do the same thing we did for the Pacific Ocean, where we do DFS on the edges. So for Atlantic Ocean, we would take this bottom row and this right column and do the exact same thing I just described for this. So we would do DFS and we would go backwards until eventually we find the same points and we return that. Our tide complexity for this algorithm is going to be O of n times m because we're visiting every single coordinate in this grid here. And our space is also going to be O of n times m because we could potentially store every single coordinate in our sets. So now let's get into the code. So here I've added the picture of the example we have in the problem, and I just put it here because I think it'll be easier to explain the code while we do it, and it'll also be easier to visualize it. So let's get started. First, I'm just going to initialize some variables. So first we're going to have our number of rows, and that's going to be equal to the length of heights, which is our array. And then I'm going to initialize the number of columns, which is the length of heights at the first index. And now we want to initialize our sets for the Atlantic and Pacific Ocean. So we'll do Pacific and Atlantic, and we're going to set them equal to empty sets, and that's just how you do it in Python. And in these sets, we're going to store the coordinates that can reach either the Pacific Ocean for this set or the Atlantic Ocean for that set. From here, we just want to define our DFS function. So we're going to call it DFS. And what are we going to pass? Well, we have to pass a row, a column, a previous value, and we also have to pass the ocean set. So I'm just going to call it ocean. And we can just skip this part for now. We'll define it in a second. And then next, we want to iterate through the left column and the right column, and also our first row and our last row. So the way we're going to do that is just do a for loop. So for column in range of columns, we want to call DFS for each one of these cells. So for example, we want to do DFS for this, this, and this, and same thing for this column here. So our row is going to be 0 for the left column, and we're going to do whatever column we're at currently. And then our previous value, we can just say is -1 for now, because to the left of this would just be the Pacific Ocean, and that has no real value. And we can put -1 because in the constraints of the problem, we're told that the height is never going to be negative. And also the ocean we're going to pass is Pacific, since that's the one that's next to it. And then we do the same thing for the Atlantic one. So DFS, but instead of 0 now, we're going to be at rows -1 because that would be the leftmost row. And also we're going to do it for each column. And again, we're going to pass -1 as the min value. And we're going to do Atlantic this time because that's what we're looking for now. And then we do the same thing, except now we do it for the rows. So we're going to start for this first row, and then we're going to do this last row as well. So for row in range of rows, we want to do DFS for the current row. And first we can do the top row, so we can just say the column is 0, and we can pass -1 as well, and this would be the Pacific Ocean. As you can see here, the first column is next, or the first row is next to the Pacific Ocean. And then we do the same thing, but for the Atlantic Ocean. So row, and then it's going to be the bottom one, so that would be columns -1. And then we pass -1 again, and that would be for the Atlantic. So now we can define our DFS function. So to start, we have to do some checks. We want to make sure that we're not passing any out of bounds. So we check if row is less than 0, or column is less than 0, or if row is greater than rows -1, or if column is greater than columns -1, then that means we're out of bounds, and we can just return. Another check we have to do is check if it's in our hash set already. So we want to check if the coordinates, row, and column is in our ocean set, then we also return, because that means we already visited it. And the last check we have to do is we have to check if the current coordinate, so we would do heights at row and column, if that is less than our previous value, then that means we can't actually traverse this, so we would just return again. And then if we make it past all these checks, that means it's a valid coordinate and it does flow into the Pacific or Atlantic Ocean, whatever we're looking at currently. So we want to add that coordinate into our set. So we would do ocean.add, and we would add our coordinate row and column. After this, we want to do DFS for the coordinate above, below, to the left, and to the right. So First, we can just do DFS, and let's say we're at this leftmost coordinate here. To go above, we would do row -1. So I can just say row -1. And then our column is going to be the same. Our previous value is not going to be whatever our current value is. So that would be heights at row and column. And last, we'll pass the ocean again, since we're going to be looking at the same one. So that was for above. For below, we just do row +1, and then we copy the same thing we just did. And similar thing for the left and right. I'm just going to copy and paste it now since it's a little bit faster. And instead of row +1, we're going to do column -1 and column +1, because that would be the left and the right values. And then after this, we should be able to traverse every single cell, and at the end we can just return our sets ANDed with each other. So we would do Pacific ANDed with Atlantic. And what this is going to do is return a new hash set that only has the common values between the Pacific set and the Atlantic set. So for example, if we look at the picture again, it would only return these yellow squares, even though it probably has a lot more coordinates in it. But these are the only squares that intersect, so that's what it's going to return. And now we can submit the code. So as you can see, this code is pretty efficient, and I'm not going to go through the code manually because it is a lot of code, as you can see here, but hopefully you understand the concept behind it. If this video helped you in any way, please leave a like and subscribe. Thanks for watching, and I'll see you in the next video.